features. I looked at pitch. I looked at temper and pitch. I looked at, what were the other ones? What was it? That frequency, I guess, beats per minute. I looked at all those different things, and pitch was the most effective. I think in combining pitch and timbre were the two most effective ones. That's what I did. I played around with the features. There's 600 and something of them, a lot of them. A lot of them fall under certain categories. But anyway, that's a good question. And kind of as you said, a lot of it's art, you know, yeah.
Since the internet is switched off, I mean, they stopped the event or something, somehow they have not filled up for. So try to do the HD guest account.
Okay.
Yeah.
Okay, let's go ahead and move forward, you guys. We're going to be cutting it close, but we'll still, if you need to go, you need to go. But I'm going to get through this real quick. So first of all, I'm not going to talk about algorithms really. I'm going to cover just a couple of things. I want you to get a good intuition about machine learning and deep learning and all of that. So when we talk about artificial intelligence, most of the time we think of a machine performing cognitive abilities that we usually associate with humans. As you can see, perception, reasoning, problem solving, even creativity. That's kind of what we think about when we think about artificial intelligence. So just so you can see, artificial intelligence sits on top, and a subfield of artificial intelligence is machine learning, and the subfield of machine learning is deep learning. Okay. Let's talk a little bit about machine learning and classification without getting into any specific algorithm. This is pretty much how a classifier works. A classifier tries to create what's called a decision boundary, where if you're on one side of the line, it's going to put you in one class. This is the song I like. If you're on another side, it's going to say this is the song I don't like. So it tries to create a decision boundary. They're usually a linear and some are non-linear. They don't always have to be straight lines. But that's what a classifier is trying to do in traditional machine learning. So let's say we have some data like this, just data that's plotting. And again, you guys, I'm showing you data that's in 2 dimensions, but data can be in thousands of dimensions that we can't visualize. Every feature is a dimension. Okay? So we have this. The algorithm might say everything above the line is blue class, everything below the line is a yellow class. And then it's going to say, where's my error? So I got 5 wrong. It's traditional machine learning. So it's going to look at its error in some way, 25% wrong. It's going to try to adjust those coefficients. Again, that's the learning part. And it's going to draw a new line. It's going to look at its error again. It's going to say, oh, I'm 15% error now. Okay? So it's going to change those it's learning. Changing its weights, coefficients again, it's going to draw a new line. Now it's saying, I'm at so it found a solution. That's largely how traditional machine learning works, where it tries to draw a decision boundary to say if you're on this side, I'm going to predict one class, or on this side, I'm going to predict the other class. Okay, now let me talk a little about neural networks, which is still a part of traditional machine learning, but is the basis of deep learning. So it's going to kind of cross over between the two. And it is today state of the art. It can learn probably any function if you give it enough data and you have enough time. Neural networks are incredible. Okay, so I want you guys to get some good intuition about that. Loosely based on the human neuron, some of you guys may have remembered from biology. Inputs come in through the dendrites, and again, depending on how much you use it, like if you type, the more something's used, the more the weight will be heavier, bigger, stronger. If not, it will be diminished or inhibited if you don't use it a lot. That's how the human brain works. So it takes in that input, it takes a weighted combination, because all that input's weighted depending on how much it's used, how important it is to the task, it weights that. All of that comes into the cell body, is transformed in some way, then it's sent back out along the axon to the next neuron. That's how the human brain works. This is an artificial neuron. Similar, you have X. You guys know what the X1, 2, and N are? What are those? Features. Those are our features. Those are the inputs. You guys know what the W's are?
Weights.
Weights. Now tell me about weights. What do those weights mean? Based on what I just said, what do those weights mean? If we go back to how does the human brain work? What do those weights mean? Importance. If something is very important to solving that problem, it's going to be a big weight. If it's not important, it may be a 0. If it hurts solving that problem, it's going to be a big negative number. So those weights are learned and they're significant. It's a weighted combination. Okay, so it's weighted. It depends how important that feature is. If that feature is very important to the prediction, it's going to have a big weight. Okay? And then, so you get that weighted combination, you're going to sum it in that neuron. You're going to transform it in some way that's going to send out to the next neuron, the next layer.
Where do the weights come from?
The weights are learned. You start off with just random numbers, and that's what I'm going to tell you as we go through this. You're going to find out the magic of neural networks. They're incredible, what they do. What we have to do with traditional machine learning, we don't have to do with neural networks. It's incredible. So this is a perceptron. This is one node in a neural network called a perceptron. Okay? So again, we have our inputs that go into that perceptron. We have these learned weights, depending on how important they are. All those are summed in that neuron. As you can see, that's the function. They're all summed in the neuron. Okay? And that's perceptron. That's just one node of maybe thousands plus in a neural network. Okay? This is the neural network. This is several perceptrons. Okay? And a lot of times you will see in the libraries in here, multi-layer perceptron is the same thing as a neural network. Okay? That first layer, our features are called the input layer. The hidden layer are the nodes in the middle, and the reason it's called a hidden layer, we don't know what goes on. We don't know what it's learning, and that's the great thing about neural networks. Let me back up and give you guys some insight here. Because right now I'm trying to differentiate traditional machine learning from deep learning. With traditional machine learning, remember what we had to do? We had to clean the data. We had to choose good features. We may have to do some feature engineering. We don't do any of that with neural networks. Neural networks learn what they will learn. We don't have a clue what they're learning. If you looked at it, it wouldn't even make sense. You'll see in a minute how you don't know what it's doing. But I hardly have to touch the data. I hardly have to clean it, partly because of the problems we work with. But it learns what features it thinks are important. And so it's a totally different paradigm using neural networks. And then you have the output layer, and that's where the prediction will come. So the input layer, that's our features. The hidden layer, it learns whatever it wants to learn, what it thinks is important. I'm going to illustrate in a second. And then you have the output layer. Okay, so let me give you a good example here, and I want you to get this because it's what's significant with deep learning. Let's say we have a data set here. We want to predict whether someone will get an on-site job interview. They're looking for a job, they give their resume, they do a phone screen, right? So we have their gender, we have their years of experience, and we have how well they were rated on their phone screen. Okay, and then we have our target values, because it's supervised, we can see who got an on-site interview and who didn't. So as we get new people, we can kind of look and make some predictions. Okay? Features, you gotta remember that. Target, you gotta remember all that. Okay? Now this is our multi-layer perceptron, neural network, artificial neural network, all the same thing. These are our features: gender, experience, and phone interview. Okay? And we're gonna predict whether they will get an on-site interview. Okay? Let's pretend, because we don't know, remember, what features are we going to put at the hidden layer? Anyone, what features will we put at the hidden layer?
All of them.
Come on, you guys.
More features?
We're trying to differentiate this from everything else. Remember what I said? We don't do anything. It learns what it wants to learn. We don't have to do anything. It learns what features it wants to learn. So we don't do anything. That's what's called the hidden layer. We don't know what's going on there. The reason I'm highlighting that is because I'm speculating. Let's say it wants to learn pay. Let's just say we don't know that. I'm just saying let's assume that so you can see how it works on the hidden layer. Let's assume that it's going to take gender, experience, and phone interview, and it says pay is an important feature. So I'm going to try to learn pay. Let's just say it's going to learn that. So it looks at gender. Gender maybe doesn't have a big impact. We already found it doesn't have a big impact on pay. Experience probably has some impact on pay. And a phone interview may have some impact on pay. So if you look at those arrows, those are kind of the weights. You think of what's most important to pay. Okay? And so let's look at the next one. Let's say it wants to learn fit. What's the fit of this person for this position? Gender may or may not have a difference, but let's say they had males don't do well in this position, or they quit often, or whatever. That might be a negative number, a negative weight there for gender there, if they had a problem. Experience might have some part of pay, and phone interview might. But phone interview would probably be the biggest part of being fit for that position. Okay, and let's say again on this next one, again, I'm just speculating, we don't know what they're learning. Let's say it wants to learn aptitude for the job. So gender may or may not have a big contribution to aptitude. Experience might, and phone interview might. So you might have something like that. Again, those are the weights because it's trying to learn some feature. We don't see that because we don't know what it's learning, but I want you to get some intuition about the weights. It's learning something, and those weights are contributing to whatever it's trying to learn in that hidden layer. Okay? And then if we want to, you could add another layer. And that's the great thing about neural networks. It learns features, then it learns features of features, then it learns features of features and features. That's why it's so powerful. You put all of that together. I'm not going to go through this, but let's say it wanted to say, How quick can the person contribute? How quickly can they come in and do the job? Or how long? What's the prospect of them being here long term? Moving up in management, are they going to be someone who probably be gone in 2 years? Well, let's just say those are features they didn't want to. I'm making these up, but that's how neural networks work. Okay, it's just going to learn whatever feature it finds important, and whatever based on your feature that you're inputting, it's going to say what are the significance of those to what I'm trying to find out.
So I just want to make sure I'm reading this correctly. So in the first hidden layer, when it was making A1 and making aptitude, you know, it wasn't actually making aptitude. It just happened to decide that a combination of a bunch of phone interview and some experience and not much gender was predictive. So it liked that.
Yes.
And
I'm just giving a name to it, but you're right. It doesn't have a name. It's just
that's-
learning a feature. Excellent. Yes.
Okay, and so when it did pay and it was like lots of experience
Yes.
and a little bit of this, it was doing the same thing.
Excellent.
It just said,
You got it.
this weight
Yes.
we like.
Yes. I
Okay.
should have had you say it that way.
Okay.
It's great. No, I'm giving it a name. It doesn't have a name. It's just learning. It's learning something that's, as he said, is predictive. I'm giving a name so you guys can see that it's something. But we don't know what it is. It's learning whatever it thinks. It may not be anything that would make any sense to us why that's important to telling us that that's a cat. But somehow that's important.
You are going to decide how many
Yes.
hidden layers.
Yes, and those are called what? When you decide, those are called hyperparameters.
Okay.
Yes, those are hyperparameters you decide. You decide how many nodes are in the hidden layer and how many hidden layers there are. That's your decision. Okay? And it comes from experience. Well, I'm mentioning more is not always better, and I'll give you an example right here. This is logistic regression, traditional machine learning, where it tries to linearly separate the data. I don't know if you can see this. This is kind of moon-shaped data, and it's not linearly separable. But when you look at neural networks, you have 1 layer, 2 layers, we get to 3 layers. It can, like I said, it can solve just about any function with enough layers. But if you get too many layers, just what I said earlier, you can overfit. You're starting to memorize that data. The peculiarities of that data, you're getting too specific. So more is not always better. And it can take a long time to train neural networks.
So this one might be just a bit too technical, but what is the entropy storage capacity of a neural network?
What do you mean by that when you say entropy?
Meaning, so the reason why you want to keep your hidden layers low is because you don't want to give it the capacity to overfit, right? You essentially want to make it stupid enough that it can't learn your data, but smart enough that it can learn the overall pattern.
So
How do you go
overfitting?
about calculating empirically how much information your neural network can store?
What I'm saying this, it depends, you're talking specifically neural network, or because if you're looking at, what's the term I'm using, in terms of information gain. I don't know if you're familiar with what information gain is. It depends on what the feature is and how much That's why neural networks don't scale well. And I'll give you an example. See, all those are weights that have to, those are parameters that have to be learned in somewhere, have to be managed. This is a classic in this database for handwritten digits. If you want to predict from handwritten digits, like maybe in the post office or something, right? These digits are all just grayscale images, right? 28 by 28 pixels. If we want to do a neural network on that, as you can see here, we have to have 20, and when we do, for example, an image like this, we see it this way. What a neural network sees it is rounded, or just flattened all the way out. So we have 784 features. Each pixel is a feature. Okay, so it's routed out, each pixel in one long that's put inside the neural network. But let's say we have images. Just 1 megapixel image, which is really relatively small today, right? You have 1 million weights. Okay, and if it's grayscale, I mean, if it's color, you have 3 channels, so it'd be 3 million weights. And that's for 1 hidden layer. I mean, for 1 unit per hidden layer. Let's say you had, you guys know what I mean by units, how many are in that hidden layer? Let's say you had 1,000 of those. You have 3 billion weights. It would be infeasible. So neural networks don't scale well. They're very good for certain problems, they don't scale well. That's why we have deep learning. Okay? Deep learning is an architecture. Okay? It's not necessarily just having a bunch of layers, it's an architecture, and I'll kind of show you what I mean by that. With traditional machine learning, we have structured data. Data just in tables, rows, columns. That's traditional machine learning that we've been doing most of the time today. There's no spatiality in terms of relationship. What I mean by that, if you put gender first, does it change the data? No. If you put the first row last, does it change the data? Doesn't. But with deep learning, we tend to use unstructured data. And unstructured data, audio, like we saw with Spotify, images, text, that's where deep learning excels because of its architecture. When we go back up here, oops, this is called a fully connected network. Everything is connected to everything else. You have to have all of those weights. Okay? But deep learning is not, so you don't have to kind of get around this problem a little bit. Let me get that down here. 2011, we did pretty well with photo recognition. Okay? But sometimes when the face was obscured or the lighting changed, it didn't do as well, or it was a drawing. We can see that that's a face, that's the same person. Machine learning couldn't do that in 2011. That was often a problem that you would have. Or if you have a picture like this, just crumple it up, we can still see it's the same person. Couldn't do that then. So that was often a problem in a lot of the algorithms. 2012, here's the gold standard for computer vision or for deep learning in terms of images. It's called the ImageNet. The gold standard has 450,000 images, 1,000 classes that a model has to classify. And you're talking about 120 different breeds of dogs. So it's a very tough problem. 2011, the error rate was 25%. So 75% accuracy. In 2012, when the convolutional neural network was introduced, it was reduced to about 16%, so you got about 84% accuracy, and that's largely what put deep learning on the map, is doing problems like this. So deep learning versus traditional, you can see 41% increase in image classification, 27% for facial recognition, and 25% for voice recognition. So let me point out a couple of things to you here that I want to make sure you guys understand. The quantity of data, we've been talking about how important the quantity of data is. For traditional machine learning, it uses it up to a point for whatever reasons, if it doesn't know what to do with the extra data for traditional machine learning. With a medium-sized neural network, say with 2 hidden layers, it likes data, but at some point it levels off also. But with deep learning, it only likes a lot of data. That's when it does its best. That's why Google gives everything away for free. Because data is gold. Data is so important. Most people can't get that quantity of data. You have to have companies like that that can get the quantity to learn the tasks that they learn, such as Siri and Facebook's face recognition and all those different things, because you have a lot of data. Keep in mind, you hear relatively small training sets, right? Thousands, tens of thousands. Doesn't really make a difference. That's not a deep learning problem, right? Whether you use logistic regression, support vector machine, or relatively small neural network, it's only when you get to a lot of data where deep learning really becomes excels. Doesn't mean you can't solve some problems, but it excels with a lot of data. You guys know what that is? Instantly. I just love that, how our brain somehow, even kids, I said babies and 2-year-olds can recognize people like that. You have shades of it. We just regard all that for whatever. You don't even think about it, you just disregard. You know what it is instantly. If we can do it without thinking about it, and logic, deep learning can do it at least as well as we can. There's not a lot of logic involved in thinking. So that's why a problem like this has been solved a long time ago. Machines are at least as good as we are on these problems. Machines see it this way, though, remember? Machines see numbers. They don't see this at all. This is what a machine is seeing. They have to recognize who that is from these numbers. Pixel intensities. Okay? You guys know what that is? It took you a fraction of a second. A 2-year-old will call that a zebra. See? But we know enough to think we have enough experience. That's a tougher problem for deep learning, but it can do it. You guys know who that is on the left? Anybody? See, without context, that's hard for us. Deep learning can do that. That's Jimmy Fallon. See? Without context, you guys couldn't do that. So those are certain problems that deep learning can excel, can do better than we can. Those are tough problems. When you don't have context, it's a tough problem. If you had context, or if you're watching the show, of course that's it. So those are problems. That's why deep learning does so well. Convolutional neural networks, which is best for perceptual tasks. Anything that can be visualized, doesn't have to be images. The Spotify problem, done with convolutional neural networks. Anything that can be visualized, for the most part. Okay, image classification, face recognition, video, music, all of that. Okay, so it's good for our Image classification, if you notice those numbers, those are probabilities that it's that type. It doesn't say who the person is. It says that it's a person, or that it's a horse, or that it's a car. So it's great at image classification. The location of an image is good for all of them. Of course, recognition of an image also. So when I said deep learning is an architecture, this is what I mean. This is what convolution, don't worry about understanding it. I want you to see a little bit. You'll get a little intuition in a minute. This is what convolutional neural network is. It takes the input with a say a photo. That has 3 layers because it's an RGB image. And it performs a convolution. Don't worry about what that is. It's a mathematical function. And then pooling, convolution pooling. I'll give you a little intuition about that is. But the reason I'm showing you this architecture, remember I showed you the fully connected network earlier and all those weights? It doesn't get fully connected to the very end. That's when you start to have that. It gets smaller, 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 so we have less weights and less things to deal with. It gets smaller. It's localized in terms of how it functions, and then it gets smaller, and then it goes into the fully connected layer. I'll try to give you a sense of that. Now, convolutional neural networks do something that's called a filter, or a kernel. Let's just say a filter. Usually it's very small, like 3 pixels by 3 pixels. And it's looking for something, remember? We don't tell it what the filter is, it learns it. And it says, I'm gonna look for a little loop. I'm gonna look for something that's slanted. I'm gonna look for something that's triangle shaped. It learns what's important. So this gives you an example of a filter. Just looking just for vertical. And areas that are bright says that feature is in this image, and if it's dark, it says it isn't. And what it does, it takes that filter and just slides it back and forth over that whole image. That's what a convolution is. And at the end of that, it has a feature map. And that map says, this is the map of where vertical is in this picture, or horizontal, or loop, or inverted U, whatever shape it's looking for. And the same thing with horizontal. And these maps are stacked up on each other. So you have one filter, here, another filter, another filter, and all these are stacked up on each other. Okay? These are what learned filters look like. Remember I said we don't know, we don't have a clue what it's learning. How does that have to do anything with a face or anything else? I have no idea, but that's what it learns. Now we're seeing them out like this, but remember all of those are stacked on top of each other. As many as there are, that's the depth of the convolutional layer. Okay, these are filters that are learned. So it has a little bit of a blob, a little bit of this shape. And what it does, maybe let's say it's a face. That first convolutional layer might just learn edges and corners and different things. Remember, all these are stacked. We're looking at them like that, but all these are stacked. Then the next will start to put those together, conform, you see a little bit of a nose, maybe an ear, maybe eyes, and finally start to recognize faces.
So this would be the next layer?
Yes, this will be the next, or somewhere down the line, but it will be subsequent to that. And then you would have this at the end. And once you get down, ultimately, then that's fed into a fully connected neural network at the end. Okay, so let me give you a little bit of intuition now. So you hear the term convolution. You don't have to be intimidated. Here's what a convolution is. You take a filter, remember, we just want to see where is that square shape, or whatever shape it is. We go all the way down, and wherever that shows up, I now have a feature map of where that feature is in this. And that's that. Now I take another filter, I do the same thing. I take another filter, I do the same thing. And all these stack up, I have all these features that are very important to whatever problem I'm trying to do. Okay. The next thing is, go ahead.
So in that last case, you're taking the filter and you're running it over each pixel to generate your content?
I'm running it, yeah, well, it's a pixel plus there's some pixels around it. Because usually it's a 3 by 3 area. The pixels are centered on that 3 by 3. And you're just going all the way back and forth. And that pixel, I don't get into what a convolution is, but yes, in essence, that's what it's doing. Yeah. Okay. So let's talk about what pooling is. So now you guys know when you see convolutional layer, what it's doing, just feature map stack. Here's what pooling is. It's just downsamples. So downsampling, really, so you lose about 75% of the information. Okay, so it's downsample, so we don't have to have as many weights. It takes the most salient features from that we got from that feature map and then downsamples it. So remember, convolution adds layers, pooling makes it smaller. More layers, smaller. More layers, smaller. That's what convolutional neural network does. So you can see image, feature maps, pooling makes it smaller. We do that continuously. Here's an example. Picture of a boat, convolutional layer, let's say there's apparently 3 filters used, so there's only 3 depths of feature maps. Pooling makes it smaller. Convolution, we have more features. Pooling makes it smaller. And then that's fed into a fully connected neural network at the end. Okay, so your convolutional neural network, anything that can be visualized, it's outstanding at that. Okay? State of the art, as I said, is Facebook, and this is what they use, the convolutional neural network that's fed all the way with convolutions pooling all the way at the end. And what they do that's a little bit different, a trick that Facebook does is called deep face. They frontalize that image. They use a 3D map to take an image if someone's in profile or anything, or slightly off, and they'll rotate it so it's frontalized. Then they can apply that convolutional neural network to it, and that's state of the art, 98% accuracy, which is at least as accurate as we are with faces. So you have something like this. Doesn't matter then. You can be in shadow, you can be in profile, you have a full beard, glasses, hat, it doesn't matter. Facebook is that good with the image, that's important to them. And so they are state of the art when it comes to facial recognition. It doesn't matter, they can recognize all of those, and you too. You guys all have your profile on Facebook also. So here's another thing that just show you about convolutional neural networks. They use forensic sketches where someone tries to sketch maybe a crime that was done. It will learn these, and then in some success that they've had, as you can see here, they would go to mugshots and identify people from these forensic sketches. Another thing is using synthesized photos, which is convolutional neural network, with also called generative adversarial networks. And what they would do is find a sketch. They'd go into mugshots and identify people who look similar to that sketch, and then they would synthetically create these photos. Now, the photos in the red box, none of those are real. Those are generated. And then quickly, this is the Spotify that I mentioned earlier, and they use what's called latent features. What I mean by latent features, not the artist, not popularity, but things I said earlier about tempo and pitch and timbre and all of that. It uses that. Let me go. I'll just finish up this one. This is called a spectrogram, and it will feed that into a convolutional neural network. Let me see how we do time. Okay. Last thing, one thing that I'm working on has to do with where people will recognize a person's social background from their voice recognition. There's a lot of research on that, where they can recognize a person's race or social background and all of that. So I'm doing some research using convolutional neural networks to do that. And then quickly, recurrent neural networks, just so you guys will at least heard of it. Recurrent neural networks usually have a sense of context. So let's see, a standard neural network just kind of goes forward. Recurrent neural networks have some sense of context and memory. So for example, may I have your, how would you finish that sentence? Anyone else? Good. It depends on context. That's what's good about convolutional neural networks. It's amazing. When convolutional neural networks will take every word and have a probability of what will come next, and whatever has the highest probability, it will guess. So if you're at school, it might be having to have your attention, right? If you're in a club, it might be have your number, right? If you're at a ballet, it might be have your keys. It totally depends on context. The convolutional neural networks are really good at those types of things, speech. And then here's an artificial neural network that was trained on first four Harry Potter books and one chapter, because it has a sense of learning recurrency and knowing how learning a writing style. You could write this. This is strictly written by neural network. Okay. Quickly, real quick, TensorFlow is largely used for deep learning. It can do other things, but it's largely a library for deep learning. It would be TensorFlow, and also Keras, which sits on top of TensorFlow and kind of abstracts it away. Don't worry about that. When you hear both of those for deep learning. And then this is the data stack for Python. Okay, this is what's called the data stack for Python. The library is NumPy, which stands for numerical Python. Pandas, which stands for pandas and data analysis. Matplotlib. Seaborn is a way to make it a little bit clearer. Then scikit-learn, which is the most common machine learning algorithm for Python. And let me also say, Python is the language related to machine learning. The language, de facto. Doesn't mean you can't do other, but today Python is just taking over. So make sure you know Python also. Okay, then real quick, I'll skip this when we get to the code. I just want to show one other thing. When we talk about this data real quick, if you guys have to go, it's okay. It won't take that long, but if you need to go, that's okay. But this is the data we're looking at. It's the classic data set where it's just looking at different types of irises and looking at their sepal length and width and the petal length and width. Real quick before we go to that. Anyone know what the 5 biggest companies are in the world?
5 biggest companies in general? Apple, Google. It depends on the context, right? biggest and what's that?
Apple just crossed $1 trillion about a month or two ago. First company ever to do it. The 5 most valuable companies, Apple, Amazon, Google or Alphabet, Microsoft, and Facebook. Right? Apple counts for all of that, of the Dow 30 and like they don't know about stocks, but Apple dominates. Here's another thing I want to say. A month later, Amazon crossed $1 trillion. It had never happened before in the history of the world. Apple did it, and Amazon did it a month later. But look, most people think of Amazon as being a store. Amazon Web Services, where they make their money, data. That's Amazon. Look at Walmart, all those companies. They're as big as all those companies combined. And the reason I showed you is this last thing I'm going to show you. Amazon and Apple, to encourage you guys, Amazon and Apple symbolize the growing influence of tech companies on markets and the economy. The industry is amassing wealth and power, creating a new order of business where the most valuable resource is no longer welded data. So you're in a great place, you guys. That's why I want to show you that the data. If you can handle data, you'll always be employable and you can do very well. I just want to show you that that's so important. So let me move on, you guys, to if you guys have a moment, if you need to go, I just want to show you a little bit of this. I don't know why this shrunk down, but